In this video, I'm going to talk about some useful properties of the delta function. So we've already got this, this picture of the delta function. Let me just redraw it here. So this is a delta function, not the delta function itself, but this is d of tau for a small or large value of tau. And then as I decrease tau, we get this spike behavior, and so this is just a reminder of what this looks like. So let's just write down some obvious properties that we should be unsurprised by. So for example, the integral of delta of t from a to b, there's two possibilities. So the first possibility is that the area under this is going to be 1, and that's going to happen if a is less than 0 and 0 is less than b. And the other possibility is this ends up being 0 if that's not the configuration. So if both a and b are negative or both a and b are positive, then we don't pick up anything from the delta function. And what I've done in calculating this is a little bit of a cheat, and I'm not going to go into the details of why this is legitimate. That would be something that you would cover in a functional analysis course. But this thing is really the limit as tau goes to 0 of d tau of t dt. And what I'm doing is I'm pulling that limit out of the integral and taking the integral of d tau of t, which is equal to 1, and then I take the limit as tau goes to 0. It doesn't matter. No, for any tau, that's going to be equal to 1, and so this is why I ended up with 1. So I'm going to do this for a few different things. So let's say we now take the integral from a to b of some function f of t multiplied by delta of t, dt. And so this will be, now as I did before, I'm going to actually pull that limit out without going into the justification or what's going on when I really do that. And this is going to be f of t times d tau of t. And now remember that d tau of t had that heavy side cutoff at minus tau and at tau. So this really is the limit as tau goes to 0 of the integral from minus tau to tau of f of t, and then d tau was on that interval was just 1 over 2 tau dt. Okay, so if we get that far, this 1 over 2 tau is a constant, so we can pull that out in front, and basically now we're just taking an integral of little f of t. So let's define capital F of t to be the antiderivative of f. So if I take capital F prime, I get little f. So that means that I can rewrite this as the limit as tau goes to 0 of capital F evaluated at tau minus capital F evaluated at minus tau, all divided by 2 tau. And this may look a little different from the definition of a derivative that you've seen before, but it's basically going a distance h in both directions and taking the limit as h goes to 0 instead of just going a distance h in one direction. So what I mean by that is that this is equivalent to the definition of the derivative of capital F. So what we get out of this is f prime, and because the limit is taking tau going to 0, this is f prime at the origin, which is just f of 0. So what we managed to do is we use an integral multiplying the delta function to extract the value of the function just at a single point, at f of 0. All right, so that's another property. Oh, and now this was the case. This was only true if a is less than 0 is less than b. And then if a and b are both negative, well, if not this, then the integral from a to b, so this is if, the integral from a to b of f of t d delta, not d, delta t, dt is just equal to 0, because you miss the spike altogether in that case. Okay, and then one more. If you take the integral from a to b of f of t, and now I'm going to shift the delta function, so I'm going to put in t minus c in the brackets, and that gives me my usual spike, but now instead of being at the origin, that's going to be at t equals c. And so this is going to behave differently. Well, I mean, it's not going to behave differently. It's just going to behave in a different location in exactly the same way. So, so what I have now, I could do a substitution where I set u equal t minus c, but you should probably be able to figure out that this is going to give me f evaluated at c. So where you center the spike is where you pick up the value of f. All right, so that is a bunch of integrals involving the delta function. So let's do an integral that's relevant to what we're talking about in this part of the course, and that is a Laplace transform. So let's take the Laplace transform of the delta function evaluated at t minus c. And so that's going to be, by definition, integral from 0 to infinity of e to the minus st times delta of t minus c dt. And now I can do a substitution and shift it, that same substitution that I suggested up here. And so that's going to give me the integral from now when u is equal to 0, or sorry, when t is equal to 0, u is equal to minus c, and this is going off to infinity, e to the minus s u plus c times delta of u. And now this is just the evaluation. Now you can see now that for sure I'm going to include, as long as c is positive, then I'm going to get the following. I will get e to the minus sc as my result from here, because I just pull out, I'm multiplying by delta u du, and so I just evaluate this function at u equals 0, which gives me e to the minus sc. And that's only true provided that c is positive. If c is negative, then this will be 0. All right, so, and now one last comment. This is actually not just about the delta function, this is about the Heaviside function as well. And I'm going to write down, so what is the derivative of the function absolute value of t minus c? So the absolute value of t minus c, that's a function that looks like this. So I have, at some value of c here, I have a function that comes down with slope minus 1 and that goes up with slope 1. And so the derivative of this guy is going to be a function that is up until c, the derivative of that will be minus 1. And then it'll go through a sudden jump. The derivative is not defined at c, and then it jumps up to 1. So I have 1 here and minus 1 down here. And so this is some type of a Heaviside function. You'll notice the jump size is going from minus 1 to 1, so it's a jump of 2. So I can write that as 2 times uc of t, but that would start from 0 and go up to 2, so I have to bring it down by 1. So I'll subtract off 1, and that gives me this function here. So that is the derivative of an absolute value. So that what that tells you is that when you have a function that has a kink in it, like this, you'll end up with a derivative that has a jump. Okay, so what happens if you take the derivative of a jump? So let's say of u sub c of t. What is the derivative of that function? So that function is something, let's say, let's draw it out here. Well, move that over. And we'll put c there. And so I have a function that's 0 up until c, and then I jump up to 1. And so I put 1 there. And so what is the derivative of this guy? Let me just move this up a little, make some space. So that's u, and now let's put in a sketch of its derivative. So its derivative is going to be 0 here, and then it's going to be 0 again here, but right around c, in fact right at c, it's going to make a sudden increase. And so one way of thinking about this is, what if instead of the Heaviside function, I had a function that came up to here and then had a ramp in there, and I made that ramp taller and taller and taller until it was infinitely steep. So that would correspond to taking a little interval minus tau and plus tau around C and giving it a little plateau in the meantime. And the height of that plateau would increase the tighter I got. So I would have something that limits, just like the delta function, to a spike. And the amplitude of the jump is 1, so the coefficient in front of that function would be 1. In other words, just the delta function. So what I'm getting at here is that the derivative of the Heaviside function is actually the delta function. So this is equal to delta of t minus c. Okay, so those are some useful properties of the delta function, and in particular this last one here is useful for thinking about things like when you have a differential equations model for something that involves a sudden jump over a very short interval of time. So for example, if you have a tank filled with water and it's got sugar in it, and you've got let's say a pipe dumping sugar water into it, and you have some outflow at this end that you're leaving, and you want to keep track of how much is in there, so you write down a differential equation, and then somebody comes along and drops in a sugar cube. So as soon as that sugar cube gets dropped in, it's just going to cause a sudden jump in the height of the concentration or of the mass in the tank. And so that corresponds to a thing like this, a Heaviside jump. And so we model that by introducing delta functions into the ODE as a source term. And we'll see some examples of that in subsequent videos.